Welcome. This video will explain the general functions of the physical layer of the OSI model. Upper layer protocols prepare data from the human network for transmission to its destination. The physical layer controls how data is transmitted on the communication media. Learning the information in this video will assist in preparing you for selecting the physical media for your networks. The three fundamental functions of the physical layer are providing the physical components needed for data transmission, data encoding, and signaling. The physical elements are the electronic hardware devices, media, and connectors that transmit and carry the signals to represent the bits. Encoding is a method of converting a stream of data bits from higher layers into a predefined code. Signaling is the generation of the electrical, optical, or wireless signals that represent the data bits, the ones and zeros, on the media. The media might be wired or wireless, as you will see in a moment. The physical layer provides the means to transport the bits that make up the data link layer frame. This is done by encoding the binary digits into signals and transmitting these signals across the physical media. It is the job of the physical layer to retrieve these individual signals from the media, restore them to their bit representations, and pass the bits up to the data link layer as a complete frame on the receiving device. When the physical layer encodes the bits into the signals for a particular medium, it must also distinguish where one frame ends and the next frame begins. This is done by presenting specific bit patterns. The transmitting device adds signals to designate the start of a frame and the end of a frame. Only the bits between these signals are considered data by the receiving device, and the rest are ignored. Copper cable, fiber optic cable, and radio and microwave frequencies are the common forms of network media over which data are transmitted. The representation of the bits, that is, the type of signal, depends upon the type of media. For example, copper cable media signals are patterns of electrical pulses as seen here. Fiber signals are patterns of light, and wireless media signals are patterns of radio waves. Various standards organizations have contributed to the definition of the physical, electrical, and mechanical properties of the media available for different data communications. These specifications include topologies, connector types, maximum segment lengths, and the media itself, and guarantee that cables and connectors will function as anticipated with different data link layer implementations. One of the most commonly used network media is copper. Examples include coaxial cable, as used in cable-based broadband networks, and unshielded twisted pair. Most modern copper-based LANs use at least Category 5 unshielded twisted pair, or Cat5 UTP. Advantages of using Cat5 UTP are its low cost and ease of installation. A disadvantage is its susceptibility to electrical and radio frequency interference. In situations where interference is present, shielded twisted pair is installed. Fiber optic cables can be broadly classified into two types, single-mode and multi-mode. Single-mode fiber carries a single ray of light, usually emitted from a laser. Because the laser light is unidirectional and travels down the center of the fiber, this type of fiber can transmit optical pulses for very long distances. Multi-mode fiber typically uses LED emitters that do not create a single coherent light wave. Instead, light from an LED enters the multi-mode fiber at different angles and results in shorter cable runs than with single-mode fiber. Multi-mode fiber and the LED light source used with it are cheaper than single-mode fiber and its laser-based emitter technology. Advantages of fiber include longer cable runs, more inherent security, and more available bandwidth than copper. Disadvantages include higher material and installation price than copper. Wireless media carry electromagnetic signals at radio and microwave frequencies. Current wireless technologies include the IEEE 802.11 standards for LANs, IEEE 802.16 WiMAX for broadband access, as well as others. Advantages of wireless media include roaming capability and anytime, anywhere connectivity. Disadvantages include its inherent security risks and its susceptibility to electromagnetic interference. You will use your knowledge of media types and their respective strengths and weaknesses to choose the best media for each networking situation. The cost and value associated with Cat5 UTP makes it useful in most LAN situations. In most enterprise environments, optical fiber is used as backbone cabling and for the interconnection of buildings in multi-building campuses. Because optical fiber does not conduct electricity and has low signal loss, it is well suited for these uses. Wireless is invaluable in areas where running cables is not possible, or as an addition to a wired LAN to provide mobility to users. Different physical media support the transfer of bits at different speeds. Data transfer can be measured using bandwidth, throughput, and goodput. Bandwidth measures the maximum amount of data that can theoretically flow over the medium in a given amount of time. Throughput is the actual measure of the transfer of bits across the media over a given period of time. And goodput is the measure of usable data transferred over a given period of time. So, goodput subtracts all the extra bits associated with encapsulation that must travel the network to get the application data from point A to point B. As an example, consider two hosts on a LAN transferring a file. If the bandwidth of the LAN is rated at 100 megabits per second, due to the sharing and media overhead, the throughput between the computers may only be 60 megabits per second. With the overhead of the encapsulation process of the TCP/IP stack removed, the actual rate of the data received by the destination computer, the goodput, might be only 40 megabits per second. The network engineer's goal is to supply the best goodput possible through high-quality network design. You now know the role of the physical layer is to encode the binary digits that represent data link layer frames into signals and transmit and receive these signals across the physical media. It is important to understand this layer because you will be better prepared to troubleshoot problems at this layer and make decisions about which physical media to deploy in specific situations.